Good morning, Tuesday, December 16, 10 a.m. and I would like to welcome you to our today's webinar, which belongs to every one of us. We will talk about clean and fresh air. My name is Mnimal and I'm the team leader of the corporate sensor product marketing team at Rutronik. A warm welcome today to Kathleen Hobble from Sensirion. She's the senior product manager for the CO2 gas sensors at Sensirion. Welcome to our headquarters here in Springen.
Thank you so much.
Thank you to have you here. Yeah, Kathleen will, you see it on the screen already. Kathleen will talk about the newest CO2 sensor of Sensirion, the STCC4. What was the inspiration for Sensirion to develop this kind of small, you see it on the screen, it's small, really small CO2 sensor? Was there a big challenge or was it?
Yeah, I think the creation of this sensor was based on market feedback to try to make a smaller sensor to fit in as many applications as possible. But obviously it was not all easy to make this sensor itself. The technology has been used in a number of applications for gas sensing, but to really bring it into this scale for low CO2 concentration was its own challenge. Absolutely.
Well, I guess there are a lot of application potentials.
Yes.
And I guess you will show in your presentation some ideas. If there are any questions, please feel free to use the chat function in Teams, and then I would directly hand over to you, Kathleen.
Great.
Thanks again to have you here.
Thank you so much. Yeah, looking forward to talking about our newest CO2 sensor, the STCC4. To give an overview of what I plan to talk about today, first we take a step back and discuss why it's interesting to measure indoor CO2 concentration. Then why Sensirion has this latest CO2 sensor, what are the advantages, how does it work actually in the sensing principle. Then a look at how STCC4 compares to competition today, that's namely optical CO2 sensors. And then finally, as you said, Manuel, to look at the applications that we see for STCC4 in combination with SHT4X, because that's in the end what we need for minimum indoor air quality measurements. So first, what is carbon dioxide, otherwise known as CO2? This is a naturally occurring gas in our atmosphere today, and it's odorless. And as you can see in the graph here, this is actually something that's been measured for decades and has an average amount in CO2 between 400 to 425 ppm, depending on seasonal variations and local conditions. It's most often associated with greenhouse gases. That's something we all talk about today, but we're not here to talk about this. So just to knock it out of the park, what we're actually interested in is measuring actually indoor CO2 concentrations. And what happens here is that humans, like us sitting in the room today, are exhaling CO2 with every breath we take. And that causes actually a locally higher amount of CO2 gas concentration, depending on the ventilation conditions and the size of the room. You can actually have a significantly increase in CO2 concentration from about 400 ppm, this outdoor air, fresh air condition, to even thousands of ppm, where it can start becoming uncomfortable. Just to explain a little bit more behind this, so every breath that you exhale contains about 40,000 parts per million, which is ppm, as I said before. And as I said, actually can add up pretty quickly in a room. You can have only within a few minutes reaching CO2 levels above 1500 ppm. And what this means, actually, in principle, what has been shown is that when CO2 concentration rises in a room, the perception of stuffy or poor air actually increases based on surveys that have been done. And what does that actually imply? Well, first, no one likes to be in stuffy air conditions. That's not very comfortable. But it actually means you could have an increased risk of exposure to harmful compounds like VOCs, NOx, formaldehyde, or PM2.5. We just had the presentation of Sens6X, which actually covers exactly those sensors. But what you can use with CO2 as a concentration measurement is to indicate whether you're exposed to those environments where you have those larger compounds. But what else can you do with CO2 gas concentration in indoor cases? So what you can also do is use CO2 as a marker for the air freshness in the room or how much ventilation there is. And this has actually been correlated to a reduced sleep quality and lower cognitive performance. And I'll actually go into this afterward to show a bit of studies on this. It's also been used during the COVID pandemic as an example that CO2 concentrations, the higher they go, the more risk you have to exposure to viral loads in air. But this also means that even during our current cold season, you have a higher risk of exposure to flu or colds, things like this. Another interesting use case for CO2 gas concentrations is to complement traditional presence detectors and help to reduce false negatives in a room. For instance, if someone has fallen, maybe the presence detector doesn't see that, but they're still exhaling CO2. And this can then be measured by the CO2 gas sensor. What you can also use with the CO2 gas sensor is to measure whether there's changes in the local environment. And that's in combination with, for instance, temperature. So if a temperature change occurs plus a lowering of the CO2 level, that can mean that there's an open window or an open door. And finally, what you can also use CO2 concentration values is to optimize the ventilation that you have in the room or the lighting, for instance, through an appliance. And that's something that's normally very interesting, is to at one point have the best possible condition for humans, but also to minimize the ventilation or lighting to only when they're in the room. So I just want to go into these two topics. I think they're really prevalent today, and that's on sleep quality and cognitive performance and how actually CO2 measurements can help us there. So what can happen in bedrooms is actually when they're not ventilated, for instance, it can be within 1 hour they already reach quite large CO2 concentrations. And 1000 ppm is actually the generally recommended limit for CO2 values before you can start to experience adverse effects. And this can also lead to other conditions that we've seen in about 20 papers. So for instance, in higher CO2 concentration environments, you may wake up more often at night. It can take you longer to fall asleep. This is the sleep onset latency, or the SOL in the second box. You can also move more during the night, and you can have significantly less sleep. And all of this is tied to the air freshness in the room, which in these studies was measured by CO2 concentration. Here, just to highlight actually how quickly this can happen, I said before, already within an hour, you can exceed 1000 ppm if you have no mechanical ventilation. And over 8 hours, you see you can even go to 4,000 or even up to 5,000, depending on how long you sleep. And depending on the ventilation rates, it's just what you see in the different colored lines. You can have then an improvement in the CO2 level, which means you're improving the air freshness in the room. But you see that it actually takes quite a lot of change in the airflow to actually have the lower CO2 values. And actually, why is this happening? So in principle, today, more and more buildings are airtight, especially with better windows installation. And in the past, this air exchange helped to reduce the amount of CO2 that could build up in the room. But because actually we have more energy efficient buildings, which help to reduce the energy for heating and cooling, for instance, on the other hand, that means that we're actually encapsulating harmful compounds in CO2. And so that requires then a mechanical ventilation to optimize. Now, of course, poor sleep quality can turn into reduced cognitive performance during the day. But actually what's been shown is that also if you work in environments with higher CO2 concentration, you also have a lower cognitive performance. For instance, there was a study that showed that student absences when they work at higher CO2 concentrations can actually increase. For instance, this can be that they're exposed to more viral loads, which means they have a higher chance of getting sick. And as I said before, it can be pretty quick actually to have an impact on the cognitive performance if you're operating in a high CO2 condition. I have a study that can show a little bit more in detail on this. And different studies have shown that it depends a bit on which CO2 concentration. But the point that can be made is that if you are working or studying in higher CO2 concentrations, it impacts your performance. So in one study that we have found, they tested a variety of different tasks, so task orientation, information searching, strategy, and at 3 different CO2 concentrations. So for instance, at 600, 1,000, 2,500 ppm. And what they saw is already at 1,000 ppm, there was a performance drop in 6 out of 9 tasks. And at 2,500 ppm, this was an even more significant drop in 7 out of 9. And strategic thinking and taking initiative were by far the most common. So just to highlight basically conclusion is that there's many reasons to use CO2 gas sensors in your applications to really improve the air quality monitoring you have and potentially even impact then the ventilation you have in the room. Now I want to talk about why we have the STCC4 as a sensor when there's already optical sensors on the market. So Sensirion itself has been working very hard in miniaturizing all kinds of different sensors because we believe that the miniaturization is really important to driving their integration into products. So we've been working in the past on miniaturized temperature humidity sensors, VOC, NOx, and particulate matter, as we saw in the Sens6X. And actually in the last years, that's also what we've been doing in our CO2 sensors as well. We first started with an NDIR optical CO2 sensor. That's, I think, a traditional product on the market, but we ourselves felt driven to look for a break in the size barrier by coming out with the STCC4X, a photoacoustic NDIR sensor. But we also still heard the feedback that, can it be smaller? Can we do more? What can we do there? And so what we did is came out basically with the STCC4, and this is by far one of the smallest CO2 sensors on the market today. What is the STCC4? In principle, it's a sensor that is striking the right balance between performance, size, power consumption, and price. You can see already probably one of the biggest benefits is the size. And it's, if comparison, about 50 times smaller than SED4X, to give you a feeling. It has an optimized accuracy. I'll talk later what that means. And it has the potential to work in battery applications with a pretty low current consumption. And it has a pretty good cost efficiency compared to optical sensors. That's just based on the comparison of a chip-based sensor with a low amount of BOM compared to optical sensors with many more pieces there. Other features of STCC4 that make it extremely interesting, I talked about the potential of reaching low power for different power budgets. We have a simple operation mode of every second of measurement, but then if you need to work at a very low power budget, we have the option of expanding out the sampling interval. It's also SMD solderable, and you can have tape and reel packaging, so you can have high volume applications. You have a digital I2C interface, so you can have a straightforward communication with the sensor. And you have a dedicated I2C controller interface to interface with the SHT4X temperature humidity sensor. And I'll go into later why we actually need to have this, but we try to make it as easy as possible to work with these two sensors in your end product. How does STCC4 actually work? So it's based, as I said before, on thermal conductivity. The concept is in some ways rather simple, but it hides this complexity behind. So we have a sensor within this diagram. There's basically a heater and a sensor nearby, and there's an exchange possible through a membrane on a cap that we have atop the sensor itself. And the sensor is then associated also with an ASIC, which is based on the Sensirion CMOS platform, and then of course an LGA for the final packaging. So what happens is that in this air exchange, there's CO2 molecules that obviously enter into the cavity, along with the fresh air that you have in the room. And the heater then basically heats up the gas that's within this cavity, and the heat is conducted through the gas to this nearby temperature sensor. And the sensor itself is able to analyze the signal it receives and then calculate a CO2 output. What you have to understand about thermal conductivity compared to an optical CO2 sensor is that an optical CO2 sensor is directly impacting it's directly measuring CO2 molecules based on the principle that the CO2 molecules are absorbing a certain wavelength in the principle. And in thermal conductivity, what you're not doing is measuring a single gas, you're measuring the composition. And significant changes in that composition are then correlated in this sensor to CO2 concentration. Well, why we believe that works is that actually in local environments, CO2 is the only gas that's significantly changing. And that is exactly because of us doing the exhalation. Just to highlight again, just to kind of give a picture of what that means, right? So I talked about this gas composition. So fresh air is comprised of nitrogen, oxygen, argon, and trace gases. And this generally stays the same throughout the world. What are we actually then measuring specifically is the trace gases that are composed in this gas composition. As you can see in this graph, CO2 is by far the largest trace gas available, which means that any changes in this gas will still have a significant impact on the gas composition, which can then be measured by the sensor. To give an overview of kind of what we're actually measuring and how fine this sensor is managing to do it, here you see in this first graph what the thermal conductivity measurement is if you would have only pure CO2. You have a certain value, and this is significantly different than fresh air. So of course, this kind of measurement would be rather straightforward. The change in the thermal conductivity of the gas is very large. And even if you have 50% CO2 and 50% air, still the change between these two values is the same. But we're actually doing something much more difficult. So even if you have 1% CO2, that's 10,000 ppm, you still can have a fairly large change in the thermal conductivity of the gas. But we are able at Sensirion to really measure these extremely small changes in the CO2 value. So it's something that's difficult, but because of Sensirion's expertise in this operation principle, we're able to actually achieve this. So how do we actually then compare STCC4 to NDIR and photoacoustic NDIR sensors? So first, just to give a background on what those other two technologies are, right? So NDIR, or non-dispersive infrared spectroscopy, is an optical method to measure CO2. And in the past, this has been, I would say, the gold standard on the market. It's quite reliable, it's quite accurate, but it's large. And it's very difficult to decrease the size, or you have a decrease in the signal-to-noise ratio. So there's a limitation there. And that's why Sensirion came out with the STCC4X using photoacoustic NDIR, because with this technology, we're able to significantly decrease the footprint while maintaining that accuracy. However, we still got the feedback that, it's still too large. We still can't fit it into certain applications. Is there a way to have a CO2 sensor that's fundamentally smaller? And that's why, for instance, we brought out this sensor based on a third technology for STCC4. So with these three technologies, Sensirion becomes the one-stop shop for all of the applications you need. So maybe the first thing we can compare between the three types of technologies, or in the end, the sensors themselves, is the accuracy. So NDIR and photoacoustic NDIR can reach high accuracies, depends a bit on how they're operated and with their dual or single channel, while in the end, thermal conductivity-based CO2 sensors, especially in low CO concentrations, are generally not reaching the same accuracy, but they are optimized as much as possible. What does that mean? We actually base our assumption that we can do these kind of measurements on science. We did a lot of measurements to understand whether we can use STCC4 in the field. And what we saw is that after an initial operation and a low CO2 event to set the baseline of the sensor itself, actually the STCC4 seen in green works extremely well compared to the STD4X as a counterexample. So for instance, the sensor is still able to well measure whether there is an office environment weekdays, weekends, or holidays. And while the sensor is not perfect, sometimes it's measuring a bit too much or too little based on the inaccuracy of the sensor, it still achieves what we needed to do, which is to measure if people are in the room and if CO2 is rising or not. Another obvious difference between these technologies is the size, as I said before. STCC4 is quite a bit smaller than what we have on the market. Just to give you a rough feeling, STCC4 is about 500 times smaller than classic CO2 sensors on the market. And even compared to STD4X, which is one of the smallest optical sensors, is 50 times smaller. So it really brings this order of magnitude improvement, makes it much easier to integrate onto a regular PCB with a very simple process. Another point just to highlight the differences in these types of sensors is that NDIR and photoacoustic NDIR have the temperature and humidity integration on board. So as you can see actually here on the SCD30, you can actually see our SHT sensor on this. All CO2 sensors need to have temperature humidity compensation because all the principles are impacted to a certain extent by the environmental conditions. And the reason that we actually have an external compensation is because we really wanted to drive the footprint down as small as possible. And many customers already have temperature humidity compensation from Sensirion, so there's no need for our customers to pay twice for the same thing. Therefore, we externalize the temperature humidity compensation that we need, but we made it as easy as possible for our customers to integrate the two sensors together. So actually on the STCC4 are two pins available to operate and pull the data that it needs from an SHT4 sensor, and actually it can output temperature, humidity, and CO2 values to the microprocessor outside. Another difference between the sensors is how you can actually integrate them into the products, right? So for regular NDR sensors, they have to be integrated manually. This, of course, makes it more expensive to work with. Maybe you have to also have a more complicated PCB. On the other hand, actually, photoacoustic NDR and thermal conductivity-based CO2 sensors both can be automated because you can use SMD. And so high volume applications are much more achievable with these two sensors. On the other hand, as well, as I said before, there's also quite a bit of a price difference. You can also see that in some ways physically in terms of the discrete elements in the sensors. There's also differences in how you can produce them, which can make them a bit cheaper or more expensive as well. But it gives you a feeling then what temperature or price differences you can have. And the last thing to point out is actually something that all of them have in common, which is that they're all direct CO2 sensors. What does this mean? So on the market today, you have 3 different technologies for CO2 that can measure CO2 directly. And you have also eCO2 measurements based on MOX. So direct CO2 measurements, what I mean by this is that you're actually measuring changes in the gas composition due to CO2 reducing or increasing. Either it's because you're working in optical, where you're measuring basically how much light is being absorbed or not, or with the thermal conductivity, you're measuring the change in the gas composition. But with eCO2 sensor, with a MOX base, what you're actually doing is not measuring CO2 at all. What you are measuring is a VOC, which is H2 or hydrogen. And their assumption is that this is proportional to how much exhalation we have of CO2. The problem is that hydrogen can also be produced with other methods as well, which means you can have a lot of false events. We had some measurements done in the past in our canteen, just as an example, where we had a couple of eCO2 sensors compared to an STCC4. And what we see is that generally eCO2 sensors overmeasure or measure events that are not really happening. And that's just due to the fact that the sensor is not directly measuring CO2. So this is where we feel Sensirion's latest CO2 sensor can actually have a big impact, is because for those customers that want to have that small improvement in their value to end customers, then adding a CO2 sensor like STCC4 is not a significant increase on the BOM, while adding significantly more value. Let's go then into the applications. I think we've already started to do this. So in principle, there are 3 outputs that we feel at Sensirion are providing the minimum indoor environmental conditions, and that's temperature, humidity, and CO2. Right, so if you have temperatures outside a range of 20 to 25 C, what can happen is that you can have more VOCs being released from paint, as an example, or you can have possibilities of heat stroke, or on the other hand, if it's colder, maybe a weaker immune system. So in this case, it's really in our best interest to maximize the comfort in this temperature range. And the same thing is also with relative humidity. There's a certain range of 40 to 60% RH. That generally minimizes the risk of mold or mildew growth. But on the other hand, you don't have the respiratory dryness, which can help us, in principle, get sick more often. And finally, as you already saw before, there's quite an advantage to keeping the CO2 values low, or the air freshness in the room, to reduce the exposure to harmful compounds, to maximize your comfort, and to have sufficient air freshness. So where can we see these 2 sensors then going into products? What we see in one hand is into indoor air quality monitors or smart home devices. Both of these serve as a way to monitor the environment and potentially give feedback either orally or by a traffic light indicator or just in a display. But that makes it possible for everyone to know what are the local conditions in that environment. What you could also do with these kinds of devices is connect them to a home automation or building management system, which would then potentially also control the ventilation in the room as well. In a similar way, you could also integrate the 2 sensors into thermostats or room control devices. You could think light switches or things like this to measure in the same way these environmental conditions and then directly control the ventilation and do heating, cooling, and etc. You could also integrate these 2 sensors into appliances themselves and use them to actually optimize the ventilation, or at least to know whether someone's in the room or not, because then you maximize the use of the devices except when you need them actually. One example that we're happy to share today is that we've worked with Loxone to actually integrate the 2 sensors into their room control device as a great example of how these small sensors are actually able to go into a very low height tolerance product and make sure that we can actually have environmental sensors really implemented wherever we need. And you can look for more information on our website or in our press release. Great. If we want to look then at applications actually in another way, let's take maybe a residential home environment, then you can actually see where they physically could be located and how they can have an impact. So we talked before about sleep quality. So obviously one area is in the bedroom. So you can have a IAQ monitor, for example, to do these measurements, or you can have a room control device. And in a bedroom or in a children's room, for example, similarly, if they're studying in there, but the environmental conditions are not optimal, you can try to change those to make sure that they get the most out of studying, or playing is obviously important for kids. Then, of course, in dining rooms, you could be having large parties or maybe just with your family, but that can mean that the CO2 values rise very quickly, which means that you want to control the ventilation in there to have a good time. And finally, in the living room, you can imagine maybe you have a party, maybe watching football or something like this. And of course, CO2 values can increase a lot. Or someone has opened a window and forgot to close it. So obviously you don't want your appliances running while you're doing that. And you can use this to actually indicate what are the local conditions. So what this means is that really depending on where you are in the home environment and what you want to do, you can actually then integrate the sensors into different appliances or different monitors. So yeah, what are the takeaways from my presentation I want to share? It's really important to measure indoor CO2 concentrations. We've shown already in these studies that it impacts sleep quality and reduces your cognitive performance. It also means that you're exposed to viral loads and to harmful compounds. So it's really important to integrate these sensors where you can. We feel that STCC4 is really able to deliver this optimized air freshness monitoring with the advantages of the size and the power consumption on top. And this is really great compared to NDIR sensors that are on the market. So we really believe that this will help to create mass market monitoring of CO2. And then finally, we saw some examples of where you can integrate these two sensors. And really the world is wide open now. I think with these size sensors, you can imagine integrating them into any kind of application. We give you some examples here, but I think we really can open the door to our customers coming to us with really a very smart and interesting way to bring monitoring in. That's everything from my side. I appreciate your time. Look forward to any questions.
Very good, Kathleen. Many thanks for this very nice presentation. Yeah, as mentioned before, if you have questions, please use the chat function in the Teams event. Maybe I have a question. We heard at the first session at 9, and we will hear later again at 11 the combo model, the SEN6 series, family series. Considering about some technical and commercial aspects. Is there an advantage to use a discrete option or instead of a combo model?
Yeah,
there is something.
Yeah, absolutely. I think there can be reasons you go either way. I think if you have a very small device and you can't afford the Sen6X footprint, that can mean that you just want to put two sensors on the PCB directly. Another reason that you might want to do discrete versus the Sen6X module is if you have really the technical capacity within your company, right? So of course it might, if you're doing the effort yourself in company, maybe discrete elements are easier for you to manage. Or on the other hand, with the Sen6X, it's really easy to integrate. It's just really a plug and play solution. So I think it depends a little bit on the background. And then I think the third is that at a certain point, if you want to have a number of discrete sensors from Sensirion, well, those might take actually a quite large footprint where we actually have maximized that within the Sen6X. So I think it really depends then on what is the needs of the customers. And what they can manage themselves or not. So we try to, from Sensirion side, make it easy either way.
Okay. Thank you.
Yeah. Okay.
Okay, then if there are no further questions, I want to thank you again, Kathleen,
so much
for this very nice presentation. We heard a lot of very nice things about the really small device from Sensirion. Very innovative product, and we saw a lot of application ideas. If you have any any application, do you need any application support, please get in contact with the Rutronik sales and FAE team, and we will try to solve together with you this kind of topics, and we're happy to design in further CO2 sensors from Sensirion.
We're looking forward to working together.
Yes, looking forward. And if there are no further questions, would again thank you for the participation and wish everyone Merry Christmas.
Thank you.